Hello everyone and welcome in today's video. Today we are back with another video with the use of method of virtual work, and let's continue with this problem. And without any further ado, let's read today's task, where today we have to determine the displacement at point B by using the method of virtual work. And for this problem, EA, EI and GA is assumed to be constant. And also, when solving the problem, we have to account for bending, axial, and shear forces. And at point A, we have a fixed support, and at C, there is a roller support. And at point B, there is an internal hinge, meaning that the bending moment here is going to be 0. Let's continue with the solution of the problem, where basically we are going to have the first case, which is going to include the real beam. And as we do have this internal hinge at point B, this is going to be very beneficial for us, as we can easily determine the support reactions for our beam. So for example, if we analyze separately member BC, this member here, and we do the sum of bending moments at the hinge, we can determine the component of the vertical reaction at point C, which for this case Cy is going to be this one. Next, we take sum of forces on y direction equal to 0, and we determine the other vertical support reaction at point A. And now, as we already defined these two supports, it's going to be easy for us if we just take the bending moments at point A equal to 0, and then we determine the bending moment at point A. While as for the forces on X, we already know and can see from the picture that the support reaction AX is going to be 0, as there no lateral load is acting on the beam itself. Always it's good, for example, if you want to make sure that the support reaction which you got are correct, you can make some type of cross check by using the equilibrium conditions, and if they match, for example, if they are 0, in this case it means that our support reaction which we determined are correct. Next, we have to determine the functions where we do have discontinuities on our beam, and it's up to us to decide on how we are going to take the cut section. So for this problem, I decided to go with this cut from the right side, and then we just take or we use the equilibrium equations from the point where we cut, and we determine those functions for bending moments, axial forces, and shear forces as shown here for this first part of the cut. Next, I decided to take the cut from the other side and determine the bending moments within these boundaries, then determine the axial force function, and the same for the shear force function. Next, as according to the task, if we go back at the beginning, we have to determine the displacement at point B. Therefore, we have to apply a virtual load of magnitude of 1 at this point of interest, and then just analyze the beam, and in that case we have to determine the functions. So now let's use the equilibrium equations as we did on the previous case in order for us to determine the support reactions. But for this case we have to be really careful, because we are going to apply this load at the hinge, and the member BC in this case, it won't take any load. Basically it will just be basically this cantilever beam here, which will work in this case. Then we use the equilibrium equation and determine the support reactions. Also, as a good thing, we can do a cross check, and as we can see here, the results which we obtained are correct. And next we are going to find the bending moment functions on the beam where we have discontinuities, and taking the same cut sections as before, we determine the axial shear and bending moment functions within these boundaries where we have discontinuities on the beam. Next, I prepared here a summary of results, which is going to be much more easier when we compute into the integrals or when we use the method of virtual work, so we can have a flow and not make any mistakes. So these are the results for real beam, virtual beam, and we have the boundaries from here. The next step to be done is to apply the method of virtual work, and we are doing that to find the displacement at point B. And as well as this beam, or on this beam, we do not have any lateral forces, the axial action is going to be disregarded, as it's going to be 0. Then, by using the values which we got from the summary table, then we just apply the formula here and the bending moment function which we take from the summary table already, And by solving the integral, we are going to get that this is going to be the displacement at point B parametrically. So in order for us to make sure that what we calculated or what we did was correct, let's just go with some values. For example, if we assume this type of cross section 100 by 100 and thickness of 10, yeah, so we choose this profile. And if one wants to get these informations, they can go and look up the different standards which the companies already provide to the customers and take these values. But also for this case, I found these values from the Autodesk Robot software, and I just used these values and some values which I assume, for example, the load P, which is going to be 5 kilonewtons per meters, and this A 2.5 meters. And if we input all these values into this formula which we found, then we are going to conclude that the displacement at point B is going to be 66 millimeters. And if we compare the results with the software, we can see from the table here that at node number 2, which, as you can see here, node slash case, this is our node of interest, we can see that the displacement at this node is minus 66 millimeter, which indicates displacement downwards of 66 millimeters, which comes to say that our result, which we got from hand calculation, is correct, and this parametric value of displacement at point B for this type of beam can be used in the future by just putting the numbers. So thank you very much for your time. I really hope you enjoyed today's video. If there is any questions, please leave them down in the comment section below. See you on the next video.